In this lecture, I will discuss about doubly reinforced beams. Okay, in the previous lecture, I have discussed about the singly reinforced beam where the top bar analysis is not discussed. In this doubly reinforced beams or doubly beams, I will discuss about the analysis of top bars also. What are doubly reinforced beams? Okay, here is the doubly reinforced beam figure. Beams having both tension and compression reinforcement. Okay, you can see above the neutral axis compression is also having the reinforcement, and below the neutral axis there is also present of reinforcement. Beams having both tension and compression reinforcement to allow the depth of the beam to be lesser than minimum depth for singly reinforced beam. When we design the singly reinforced beam, then we follow the D minimum criteria, means minimum effective depth criteria. We have to follow that strict guidelines. But in doubly reinforced beam, there is no such strict guidelines. We can go below the minimum depth. For example, if the in the singly reinforced beam, the minimum depth is 300 millimeter, but for the doubly reinforced beam, we can go for 250 millimeter or even 2 to 5 millimeter. Okay, that is the main benefit of the doubly reinforced beams. Okay, beams having both tension and compression reinforcement to allow the depth of beam, okay, allowing the depth of the beam to be lesser than minimum depth for singly reinforced beams. Okay, it is allowing us to go for minimum depth as compared to singly reinforced beam. That is the main benefit of doubly reinforced beam. By using lesser depth, the lever arm reduces, and to develop the same force, more area of steel is required. So solution is costly. This doubly reinforced beam solution is costly. Why? You have seen in the previous examples, on the top we have compression force and at the bottom we have the tension force, and the distance between the two forces is the lever arm. Okay. In the doubly reinforced beam, the lever arm reduces. As the lever arm reduces, the couple force will reduce. Okay. This and this lever arm reduces in the doubly reinforced beam. So as a result, the couple or the moment force will reduce. To make or enhance the moment force, the lever arm will be remain constant, but we can increase the reinforcement. So we increase the reinforcement to make the same force. Okay, we increase the for example, we increase this force by providing steel on top, and similarly we also increase the steel at the bottom. Okay, by increasing the steel, okay, we're getting the higher force, and by higher force the couple is small, and by multiplying this we get the same moment, okay, as per our requirements. I will repeat this sentence. By using lesser depth, the lever arm reduces. Okay, by using the lesser depth of the section, the lever arm between the forces reduces, and to develop the same force, more area of steel is required. So solution is costly. Ductility will be increased by providing compression steel. Okay, steel has the property of ductility. By providing steel, we get the benefit of ductility. Hanger bars can also be used as compression steel, reducing the cost up to certain extent or certain cost. What it means, in the previous singly reinforced beams, we do not use the top bars or compression bars in the analysis. We use the top bars as just hanger bars for the hanging of ties or stirrups. But in the doubly reinforced beam, the top bars we used in our analysis. Okay, we do not use as a just for the hanging purpose. We use in the forces, and we use the magnitude of this area of steel in the analysis and design. Okay, so when we use the top bars in the analysis and design, that will also reduce the cost up to certain extent. Fourth point, for high-rise buildings, the extra cost of shallow deep beams is offset by saving due to less story height. Okay, in singly reinforced beams, we got many much larger heights. Okay, of this uh, means we get large depths of the beams. In singly reinforced beam, but with the doubly reinforced beam we can go for smaller depths. When we go for smaller depths we will get the large story height. Okay, we can use that benefit in the story height, clear story height. So for high-rise buildings, the extra cost of shallow deep beam, the doubly reinforced beam is also shallow deep beam, is offset by saving due to less story height. Okay, then we have to provide the less story height due to doubly reinforced beam. Then we get more number of stories in a high-rise building. Compression steel may reduce creep and shrinkage of concrete and thus reducing long-term deflection. In the long-term deflection formula, we have to put only the compression steel. In the long-term deflection calculations, we have to put the compression steel. Okay, and the compression steel comes only in doubly reinforced beam. By providing the compression steel, we get lesser long-term deflections. We are reducing the long-term deflections by providing the compression steel. That is the also one benefit of doubly reinforced beam. Now in doubly reinforced beam, the tension steel always yields. The tension steel always yields. Tension steel always yields in doubly reinforced beam. There are two possible cases of doubly reinforced beams. Okay, one thing is understood that compression tension steel always yield. Now remaining steel is compression steel. So there are two cases. One case, compression steel is yielding at ultimate conditions. Second, compression steel is not yielding at ultimate condition. That are the two cases of doubly reinforced beam. So here is the schematic analysis diagrams. Okay, here is a doubly reinforced beam. The width of the beam is B. The depth of the effective depth of the tension steel, that is D. Height of total depth of the beam. Okay, total depth of the beam, that is H, and the effective depth of compression steel, that is D dash. Okay, just like the tension steel, that is from top fiber to the center of this bars, that is D. Now what is D dash? In the compression steel, the from top fiber to the center of the bars, that is D dash. Okay, here is a strain diagram. In the strain diagram, previously we have only strain S, the strain in tension steel. Now in this doubly reinforced beam, we got also strain in compression steel, that is strain S dash. Okay, we denote the compression steel with dash. And at the top, that is a concrete. Okay, we the behavior we take in the ultimate analysis is same, that under the neutral axis we ignore the concrete and above the neutral axis we consider the concrete. Okay, so that's why at top fiber ultimate concrete strain is shown 0.003. Okay, the height from the neutral axis to top fiber, that is C. Now the equivalent stress block diagram by Whitney. Okay, see the equivalent stress block diagram converted into A. Okay, the concrete stress, that is 0.85 Fc prime, that is Fc prime, and the stress in steel, that is Fs dash, and stress in tension steel, that is Fs. Okay, Previously we do not have this parameter, we have only this stress in concrete and stress in steel. Now we have one more parameter, that is stress in compression steel. That is a new parameter in W reinforced beam. Now here, now we have three stresses. Now stresses are converted into forces by multiplying area. Okay, first of all, this is stress in steel. So stress in steel shown in the CS, because that area of steel is provided in the compression, so that's why it is shown as compression force with steel. The second, the compression force is concrete, that is shown with C sub C. Okay, at the bottom the tension steel, that is shown with T. Okay, T is equal to Fs, area of steel in tension, stress in steel in tension. The lever arm between the concrete and the steel, that is same, D minus A by 2. Now the new force, that is a compression steel, the lever arm is D minus D dash. Okay, here is the D from the toe fiber. When you subtract the D dash, that will become the lever arm between this steel and this steel. Okay, the lever arm here D minus D dash for CS. Now we can get the stress if we have the strain in steel in tension. Similarly, we can get the stress in concrete in compression steel if we have the strain in steel in compression. Now here are the forces. The tension steel, here T is equal to ASFS, that is stress into area of steel. Compression steel, that is AS dash into Fs dash. The compression force in concrete, that is 0.85 Fc prime BA. This parameter we already know. This parameter we also already know. This is the new parameter in the doubly reinforced beam, that is CS is equal to AS dash Fs dash. Stress in compression steel, area of steel of compression. First case, both tension and compression steel are yielding at ultimate condition. Okay, means the stress in steel, okay, in the tension steel is equal to yield, and stress in compression steel is also yielding, means tension and compression steel both are yielding. Location of neutral axis, then we will find the location of neutral axis, mean how we will find the Whitney's stress equivalent stress block depth, means A. Consider equilibrium of forces in longitudinal directions, means now these upper two forces, compression in steel, compression in concrete, these both forces will be balanced by this total steel. Okay, that's why equilibrium will exist, means this force and this force, for example this force, this is 5 and this is 10, then the tension steel will have to balance by a cumulating of amount 15. Okay, 5 and 10, then this amount should be 15. Okay, then equilibrium will exist. Okay, so here consider equilibrium of forces in longitudinal direction, means tension steel is equal to compression of concrete plus compression of steel. Okay, so now I will put just values. Tension is equal to area of steel into Fy, compression of in concrete 0.85 Fc prime BA, and compression in steel AS dash Fs dash. Now take AS dash Fs dash to the other side, okay, and divide this whole part except A to the other side. Okay, here is the formula. AS dash Fs dash take to the other side, okay, then divide this except A to the other side. Okay, and just take the common Fy, because the both tension and compression steel is yielding. Okay, then you will get A, okay, depth of neutral axis. And then you can get the C, neutral axis depth, by just C A divided by beta 1. Both tension and compression steel are yielding at ultimate condition. Now to get the strain in steel, okay, in the compression steel, we already have the expression for strain in tension steel, but we do not have the expression for strain in compression steel. Okay, so here comparing here is a bigger triangle, that is the ADE, the second triangle ABC. Okay, similar triangle, the depths, okay, uh, this depth, this AB depth, that is C minus D dash, that is C minus D dash. Now the bigger triangle depth, that is C. Okay, now here in the left side, that is strain S dash, that is smaller triangle width, and here is a larger triangle width, that is 0.03 here by similar triangle. Now take all the part to the other side, you will get strain S dash. Okay, then to convert into A, okay, you already know C is equal to A over beta 1. You will put the values and you will get the result strain S dash 0.003 A minus beta 1 D dash A. If strain S dash, if strain in compression steel is greater than yield strain, then your steel will be yielding, compression steel is yielding. If strain S dash less than strain Y, compression steel is not yielding. Now total tensile force in steel, okay, that is T equal to T1 plus T2, means these T have to balance these two forces, okay, due to compression in concrete, due to compression in steel. Okay, now this T have two components, that is T1 plus T2. One T1 is balancing CC, second T2 is balancing CS. Okay, here T1 is balanced by CS, okay, and T2 is balanced by CC. Okay, means this tension steel have two components, one to balance these two forces, one is T1, second is T2. Okay, just let's say T1 is balancing CS, T2 is balancing CC. Okay, we can also simplify another small expression that we will use in the next slides. If we have just named T1 will be balanced by CS, T2 will be balanced by C, then we can also get T2. Okay, just T1 take to the other side. Okay, this is just mathematical. It will not make any problem. Okay, here moment capacity by compression steel. Okay, moment capacity by compression steel. Okay, here is the lever arm. Now first of all by CS. Okay, the compression force into lever arm, compression force is CS. Okay, compression force is CS, lever arm is D minus D dash, that is movement force into lever arm. Now CS value is AS dash FY dash. Okay, it is FS dash or FS dash that will of the compression steel. Now second, Mn2 moment capacity by concrete, that is CC, that is T2. Okay, the lever arm for the concrete, that is same D minus A by 2. Okay, equal, or you can use T2 D minus A by 2. In the T2 I have shown in the previous slide, we can also write that T minus T1. Okay, T is the total steel, that is of tension, ASFY, minus T1 of the compression steel, that is AS dash FS dash. Okay, here now you can write full moment capacity by this section, by concrete and by steel. Okay, that is a total moment capacity. Mn is equal to Mn1 plus Mn2. Mn1 by compression steel, Mn2 by concrete. Okay, concrete is that is T1, that is T2, the T2 here, that is T minus T1. Okay, here AS dash fs dash d minus d dash plus as fy minus as dash fy dash into d minus a by 2. Now, second case, compression steel is not yielding. Okay, tension steel is yielding in doubly reinforced beam. Now, the second case is compression steel is not yielding. Okay, means it is less than stress in steel of compression that is less than yield stress. Okay, fs dash will be equal to E into strain S dash. The expression of strain S dash we already got. Okay, that is 0.003 a minus beta 1 d dash over a multiplied with modulus of elasticity. Then we got the value of 600. Now we got the fs dash value. Okay, then the location of neutral axis will be calculated as a into as fy divided by 0.85 fc prime b, and here not will be used, fy will be used fs dash. Okay, because stress is less than yield. Okay, then we can get the value of c at neutral axis depth. C is equal to a over beta. Example number 1. Example number 1, a doubly reinforced section has the following sectional properties. Area of steel in compression, that is 570 millimeter square. Area of steel in tension, that is 3042 millimeter square. D dash means effective depth of compression steel, that is 60 millimeter. B is 300 millimeter. Fy 300 megapascal. Okay, and calculate the moment capacity for the following two cases. First case, when the concrete strength is 20 megapascal and the effective depth of the section is 5 to 5 millimeter. Second case, concrete strength is 35 megapascal, means grade of concrete is 35 C35, and the effective depth is 2 to 5 millimeter.